Thank you. Nice to give a talk here. So yeah, as you can see the title, I'll talk about an application of the K-stability or K-moduli in studying the moduli curves, or actually it can be used to study other moduli spaces. So okay, so the goal for today is to understand the different compactifications or birational models of the moduli space of, let's say, smooth curves. But if you consider birational models, we always have compact birational models. Yeah. So this is our rough strategy. So you fix a genus and you consider the moduli of smooth curves of genus G. You pick a general one and you consider the canonical embedding. A priori, the canonical embedding will embed this curve into some projective space. But the trick here is can we find a surface, a uniform surface for general curve, such that the canonical embedding, the canonical image of this curve is lying on this surface, so that we can study the pairs x, c. Now c is a divisor on this surface. Here's a perfect model. So, well, this is work long time ago. So for genus 3 curve, a non-hyperelliptic genus 3 curve can be canonically embedded into the projected plane as a plane quoted curve, of degree 4. So you can consider the pair P2 come with a, well, here I put a coefficient here, and where the divisor, the boundary divisor, is the curve you consider. So this is a log final pair if the C is between 0 and 3/4, and its log labial is C is equal to 3/4, and if it is a log general type if the C is between 3/4 and 1, right? So in the first case, in the log final case, we have the K-moduli space to parameterize such a pair, and for log general type case, we have the KSB moduli developed by Kolar, Shetterberry, Alexev. And for the log labial case, this is a pretty recent work. I don't think they published this work, but the fact is they construct such a moduli space only for now, for the moment, only for the plane curve case. So another approach to the moduli of curves is by using the so-called Hasse-Q program, so which I will recall again later. So roughly speaking, you choose a, let's say, rational number between 0 and 1, such that this divisor, the canonical plus the alpha multiple of the boundary divisor delta, where the delta is the boundary divisor of the MG bar, such that this divisor is pseudo effective. Then you take the canonical model with respect to this divisor. This gives you a birational model of MG bar called Hasse-Q model, and this will depend on the choice of the alpha. So for genus 3 case, we have a very nice picture. So on the bottom, we have the Hasse-Q model, and as I said, it depends on the choice of the alpha. So when you vary your alpha, you get different models. So here are all the models you get. When alpha equal to 1, you just recover your M3 bar, the moduli of stable curves of genus 3, and you have the contraction, the divisorial contraction to the moduli of the Hilbert stable curves. Then you have a further contractions, and finally you'll end up with the M3 bar at some point. And after that, you got empty. The empty model, because the K plus alpha delta is no longer big or pseudo effective. This is by just studying the curves. But on the bottom, they study the pairs. When C is equal to 1, remember, so here we have a coefficient C. When C is equal to 1, you have this Hasse studied this KSB moduli of P2 together with a curve with coefficient equal to 1. And this is isomorphism. And Hacking studied the case where C equal to 3 or 4 plus epsilon, which is just, a little bit after the log Calabi-Yau threshold. And so for the right-hand side, this was the work by Kenny Asher, Christian Development, and Yuchen Liu. They studied the log funnel case, meaning that C is less than 3/4. And in the middle, this is their recent work, which is the modular log Calabi-Yau. So, and you can see everything are isomorphic. So they patch together to give you a nice picture of this. But yeah, and similarly, you can consider the genus 4 case. So yeah, some people are working on this. I don't know the result because they didn't tell me. But the thing is, if you have a general curve of genus 4, that's a general curve, then C is canonically embedded into the P1 cross P1. So you can study the pair P1 cross P1 together with a boundary divisor given by this genus 4 curve. And some work, there was some work by like Castaneda, Martin, and Radulaza. They studied the Haskell program for genus 4 curve. And now people, ADL and Xiaowei Wang, they are studying the K-moduli of this page. But we don't hope that this the Haskell agrees with the moduli of pairs in the higher genus case. And again, as I said, this depends on the canonical embedding you have. Sometimes you don't have a good model for the embedding. But so for today, we will focus on the genus 6 case where we have such a nice embedding. So let me first recall some result on the geometry of genus 6 curve. So let's see, be a genus 6 curve, which is general. Yeah. Then by Brillo-Neser theorem, you know that if you compute the dimension of the linear system of degree 2, the dimension 2 and degree 6, this will be equal to 0. This means that there are finite many maps for C mapping to P2 as with image a plan-sextate curve. If you compute the the arithmetic genus of the plan-sextate curve, you find that discrepancy of the geometric genus and arithmetic genus will be 4. That means that typically the image will have 4 nodes. So there are 2 cases. Either we know, okay, let me call this phi. Either the phi of C is a irreducible plan-sextate curve with 4 nodes, or C is called special. By definition, it means that the dimension of the linear system we compute is bigger than 0. So in the first case, there are 2 sub cases. One is that the 4 nodes of the image will lie on general position, meaning that, for instance, none of them are coincide with each other, and none 3 of them are lying on a line. So let's say first case is in general position. And second is they are not. So in the second case, when C is special, we still have this is a classical result. We have a classification of such special curves. Either it's a plane quintic curve. Of degree 5, if you compute the degree 5 smooth curve in the plane, you'll find the genus is equal to 6. Or it's hyperelliptic. or it's bi-elliptic, meaning that you have a 2-to-1 map to an elliptic curve. And the last case is it is trigonal, meaning that you have a 3-to-1 map to P2. That's our P1. Okay, now let's first focus on the general case, meaning that your image is a irreducible plansextic with 4 nodes in general position. In this case, if you blow up, let's say if we blow up the 4 nodes of our image in P2, you'll get a, let's say you have a blow up of P2 at 4 points. This is a smooth Pezzo surface of degree 5, which is unique up to isomorphism. Because you block 4 points, you can arrange any 4 points to the others, right? So for notation, so let's call this sigma. This is our unique smooth quintic Pezzo surface. So now the upshot is, if you are a general curve of genus 6, your canonical embedding will embed your curve into this smooth quintic Pezzo. And you can also compute the divisor class. So the C will be in the linear series of the double anticanonical. And by the way, the automorphism group of this surface is S5, the symmetric group. In particular, it's finite. So that, as I said before, if you want to study the curves of genus 6, we can study the pair. So we want to study the pair sigma comma C. Here again, I put a coefficient to make it a pair that we want. Okay, this is some fact about the geometry of the genus 6 curve. So now it's the time for the case stability. I think so. Yeah, I think people are quite know something about this. So I won't introduce too many notations or histories of that. But we know the case stability notation was introduced by Tian Donaldson for studying the existence of the Keeler-Einstein metric on the final manifold, right? And after the BCHM, we know that people started using the birational method to study the case stability, and this result culminated in the Yeltin-Donaldson conjecture, saying that if you are a final variety or log final pair, yeah, it is K polystable if and only if it emits a Keeler-Einstein or weak Keeler-Einstein metric, right? So for the completeness of this talk, I will introduce the definition of the case stability by using the evaluative criterion. This is not the original definition, but it's easier to apply. So this is the evaluative criterion, which gives you a equivalent definition of the case stability introduced by, let's see, Shili. So if you have a log final pair, and you choose any prime divisor over X. So it's, I mean, it's lying on a birational model over X. That's called as pi. Then there are several invariants. The first one is called log discrepancy, which is common in the birational geometry. It's defined by the 1 plus the order of the discrepancy of the canonicals. Roughly speaking, it measures the maximal vanishing order of this discrepancy of the I mean, the maximal vanishing order of the canonical along the center of this divisor. Another one is called the S invariant. Defined by so first we need to normalize it. It's normalized by the volume of this divisor, and you take the integral from 0 to, actually this is a finite integral of the volume of anticanonical minus some multiple of E, where you take the integral for this number T. This roughly measures the average, I mean the average vanishing order of this divisor along the center of E. So you consider their difference called the beta. Beta is still, well, it still depends on the X and D, but sometimes if the notation will omit that, if there's no confusions, it's given by the difference of them. So this is a theorem or definition. The log funnel pair X comma D. So here log funnel means that you have KLT singularity and minus K minus D is an ample Q divisor. So for this log funnel pair, it is K semi-stable if and only if the beta invariant of E is non-negative for any prime divisor over X. And is K stable if and only if this is a strict positive number. So here are some examples. So in dimension one case, you have P1, right? Let's consider only the absolute case for the moment. You have only P1, and well, it's easy to check. This is the K polystable member. This is not that interesting, but in dimension two case, X. So in this case, X is a smooth. Let's consider the smooth case. So it's a smooth the Pezzo surface. It is K semi-stable if and only if it is not equal to the blow up of P2 at 1 point or 2 points. Because in that two cases, the automorphism group is not reductive. And in dimension 3 case, I think you know this better than me. So for funnel threefold, there are 1 of 5 families. And among those 1 of 5 families, there are about 70 plus of them have K semi-stable members. Okay. This is something about the K-stability. But for us, the important thing is K-stability can be used to construct a moduli space of the log final pairs or final varieties. So this is the K-moduli theorem contributed by a lot of people. So in general, they proved that if you fix the dimension and volume, yeah, and you fix the dimension and volume, and there is a Artin stack, a separated Artin stack, parameterizing all the K semi-stable, let's say, final varieties or log final pairs with that invariant, and this is a Artin stack which will emit a good moduli space, which is a proper scheme, parameterizing all the K polystable log final pairs or final varieties. This is the general version, but for us, let me only write down the ingredient that we will use. So let's see, this is a quick version. So for any rational number C, there exists a projective scheme denoted by m bar k of C. Here I use bar just, remind us that this moduli is compact, which is very useful. And K means K polystable, and this moduli space parameterize K polystable pairs X, comma CD, where C the coefficient we choose, and we require this pair to admit a Q-Gorenstein smoothing. A Q-Gorenstein smoothing to the pair we want to consider, where the surface is the unique quintic dipedal surface, and this boundary divisor lies in the double anticanonical, which is a smooth. Okay. And you may ask, how does this moduli space depend on the choice of this C? So this phenomenon was first studied by Kenny Asher, Christian Deveming, and Yuchen Liu in 19, seeing that there exists finite many CIs, where the first one will be 0, less than C1, up to, let's say, CL, which is equal to 1/2, which is also the log Calabi-Yau threshold, right? Because we choose this C in the double anticanonical. There are finite many such numbers, such that when you choose your C, strictly between two consecutive ones, Ci to Ci plus 1, the K-moduli space is independent of the C you choose. But what about you choose C to be exactly equal to Ci? So in this case, when C is equal to Ci, in this case here, for instance, you have this Ci minus epsilon. Here we have the K moduli of coefficient Ci plus epsilon. Here we have Mk of Ci. So these are all birational. And here you have a birational morphism. Here we have birational morphism. And here you only have a birational map. Oops. Use dotted arrow. So let me call this phi minus, call this phi plus. So we know that the phi minus is a flip of the birational contraction phi plus. And if you, in particular, if you denote the E, let's say E minus and E plus, as well as the, let's say, Z to be the exceptional locus, then we have this dimension of EI plus the dimension of E minus plus dimension of E plus is equal to the dimension of Z plus the dimension of the moduli space plus 1. Here, well, it doesn't depend on the moduli space you choose because they are all birational, so you have the same dimension. So the reason is this is locally given by VGIT, the variation of GIT. So you have this equality on the dimension, and this will be used to check the whether you get all the strata after you pass this wall. So we call this sea ice walls. So any questions so far? Okay, great. So before talking about our main results, let's spend a minute to see remind that we want to study the moduli of curves, the different model of moduli of curves. So for our case, there are two of them, which are canonical. So two birational models of M6 bar. So the first one is given by GIT, because any general member in this moduli space in the M6 bar can be embedded into the smooth quintic of the Pezzo as a linear series in the double anticanonical. So if we consider the linear series of this double anticanonical, then you mod out the automorphism group, which is the symmetric group. This will give you a birational model given by GIT. So this is birational. Another way to get a birational model is via the Hodge theory and moduli of K3. So given such a pair, sigma comma C, where C is in the double anticanonical, you take a double cover of sigma, branch along C, then you'll end up with a K3 surface of degree 10. This is exactly the same construction of the double cover of P2 branch along sextet curve. Now the moduli space is not compact, but you want a compact one, so you take the Bailey-Brill compactification of that, denoted by F star, which is the Bailey-Brill compactification of the moduli of smooth K3. Here D is the symmetric domain, and the gamma is whatever the automorphism group you mod out. So this is a Bailey-Brill compactification of the moduli of K3. So now the question, what are the relations of these different compactifications or birational models of M6 bar? So here's our theorem. So let's call this theorem A. So again, remember that our K-moduli space is the, for simplicity, let's just see. This is the closure of the pair sigma comma C times a capital C with C. Meaning that general member is of this form, and you also admit some, the degeneration of a K polystable degeneration of such pair. So the first theorem says that if C is very small, then your K-moduli space is isomorphic to the VGIT moduli. And in particular, the Picard rank of this K-moduli when C is very small is equal to 1, because this is a finite quotient of a projected space. The second one, when C is large, meaning that it is close to 1/2, then you have a morphism, you have a birational morphism from your K-moduli to the moduli of K3, the Bailey-Biro compactification of that. And in fact, this is an isomorphic in codimension 1. And this is, in fact, the ample model. So on this K-moduli space, you have a NAF divisor, a NAF polarization given by the Hodge bundle, the Hodge, or the Hodge Q line bundle. And you know that on the moduli space of K3, the Hodge line bundle is ample. So in fact, this morphism is given by you take the ample model of that, meaning you take the approach of the second ring of that. Is the ample model of the Hodge Q line bundle. Okay, so these are the two extreme cases. So what if you vary C in between? Then, as I said before, a priori we know that there are finite many walls, right? And the walls are connected by some flips. But for flips in particular, there's a particular case, meaning that if you have a divisorial contraction, then on the other side, you'll get an isomorphism. So this is next result. Seeing that among all the walls, there are exactly 3 of them which is some very concrete numbers, such that you get divisorial contractions, meaning that the phi plus, or okay, so here we use I, so let's say phi I plus to keep our notation consistent, such that this is a divisorial contraction. Divisorial contraction. And in particular, remember that when C is very small, your Picard rank is equal to 1, and after one divisorial contraction, your Picard rank will increase by 1. So in particular, the Picard rank of the K-moduli when C is large enough is equal to 4. And the last result tells you that all the AD the Pezzo surface of degree 5, dp5, will appear in some K-moduli. So this means that, so after crossing sufficient many walls, you'll get the pair where the boundary, where the surface part is a AD the Pezzo surface. Remember, at the beginning, we won't have the smooth the Pezzo surface. And after some wall crossings, you get the singular, the mild singular ones. And actually, I can explicitly tell you where does it appear. And in particular, it appears in the in the last K-moduli when C is equal to half minus epsilon. But you don't really care about these numbers. So maybe let me give you an example. So example of the wall crossing. Let's see only the first wall. The first wall. Given by 1/17. So let's draw a diagram. So here, when your C is less than 1/17, then there's here you have E minus, which is actually only a point. This point is parameterize such a pair where you have this P2 and you choose 4 points. Remember, we want to block 4 points on P2, and you draw 2 lines. So you're connecting them. So, well, I gave this 2 lines some multiplicity. So for this line, I gave a multiplicity 4. For this, I gave a multiplicity 2. So you get a plan-sexy curve passing through this 4 points of multiplicity at least 2. Then after blowing up these 4 points, you can take the proper transform. Then you get a boundary divisor in the linear series minus 2k, right? That will be polystable when C is less than 1/17. So, but when C is equal to 1/17, this pair is no longer K polystable, but only K semi-stable. And the K polystable replacement will be like this. You choose these 2 points on the line of multiplicity 2. You collide them together, or you consider the degeneration of 1 point along the direction of this line to the other point. So the limits will be like this. You still start with a P2. This E minus is a point, or it's the point parameterizes the pair given by this. And this is our Z. It's also a point. What is this? So here you still have 2 points here. You don't change these 2 points. But here, as you collide 2 of them together, you get a tangent direction. And you block these 2 points and this tangent direction. You get a weak dipedal surface of degree 4, meaning that minus K is not ample but nef. Then you contract the minus 2 curve. In other words, you take the ample model. Then you get a dipedal surface with that A1 singularity. What are the boundary divisor? Here you still have this curve, this line of multiplicity 4, and here the line is given by this tangent direction of multiplicity 2. This is your replacement when C is equal to 1/17. And after this wall, what is the E plus? So the E plus will consist of the pairs. Let's call this surface sigma 1. So let's call this surface sigma 1, which is the dipedal surface of degree 5 with an A1 singularity. The pair will be sigma 1, C times capital C, where this capital C is in the double anticanonical, and let's call this A1 singularity P, and we require this P is not in C, and also C is not equal to C naught. What is C naught? This is our C naught, given by this 4-2, the 4-2 line arrangement. This is the E plus. And if you count the dimension, you'll find that the dimension of the whole moduli space is equal to 15, which is also the same as the dimension of the moduli of genus 6 curve. And here you get a point. Here you get a point because Z and E minus are all points. And here, if you compute the dimension, you'll find this is the 14 dimensional the 14-dimensional locus. So it satisfies our, remember we have an equality about the dimension of this exceptional locus. Okay, this is some. I'll give you a description of the wall crossing structure in our moduli space. Remember again, we want to study the relation to the moduli of curves, right? So now let's consider the maps, birational maps or morphisms to M6 or M6 bar. So here you have two. Okay, let's consider this two different moduli spaces, two extreme case. So when a K-moduli space is well, when the coefficient is equal to epsilon, then your birational map to M6. Let's only consider the smooth locus, and by the theorem A1, you know that.
Sorry, can I ask a question?
Sure.
Just to wake up for myself. Can we go back to the formula you had for dimension?
Yep. Yeah. So in the first wall case, these two are both equal to the. Oh, sorry. Oh, my bad.
It will be minus.
This,
right?
Sorry. Yeah, thanks. This is minus.
And it doesn't always have to be equal, right?
Say that again, sorry.
It doesn't have to be equal for all kinds of VGIT, is it true?
For VGITs, I think yes, right? If you have a VGIT structure, then local. Oh, okay. So this is just locally.
Yeah, locally. Yeah. Yeah, but anyway, for your case, this is perfectly fine. Yeah, I think it's fine with minus. But we can maybe think about some examples in the meantime. But thank you. Thank you.
Okay. Oh, by the way, I missed well, I missed a very little thing. So here the evaluated criteria is by Fujita and Lee. I'll say okay, it's better to Fujita and Lee. It's better to give the credit. Sorry about that. Okay, so the theorem A tells you that the image will be the locus of the smooth genus 6 curve with exactly 5 G26. Meaning that if you're genus 6 curve, you consider the map to P2, then typically you have 4 nodes. Then at first you only have the curves embedded into the smooth quintic de Pezzo surface, right? So that means that the 4 nodes have to lie on, in general position. So this is what theorem 1 tells you. What about the case when C is equal to half minus epsilon? If you consider the map to M6, then the 2 and 3 tells you that the image will consist of, I should say, contain all the trigonal curve as well as the plane quintic curve. So why is it? Actually, remember that we have this 1/4 and 11/52. This two, after this two wall crossing, you'll recover most. Okay, after after this 11/52, you'll recover almost all the trigonal curve, and 1/4 you'll recover the plane quintic curve, meaning that they will appear as a boundary divisor part of a pair in the K-modular space. And also we have 4. 4 tells you that the image will contain all the real another general curve. Meaning that if you consider the 4 nodes of the plane sextant curve, they don't have to lie in general position, meaning that these curves will, I mean, if you consider the canonical embedding of this curve, it will lie on some AD-dependent surfaces. So if you recall our classification of the smooth genus 6 curve, this is our upshot. The only, okay, let's say the image of this K-moduli to M6, this is a rational map, sorry, only misses the locus, the loci of hyperelliptic and bielliptic curves. And I can also tell you where are they. So for the bielliptic cases, so remember we have the sigma comma c times 2, let's say 2c3. So here C3 is a cubic curve. It's let's say a smooth plane cubic curve, which is an elliptic curve. And the 2 multiple of them is a plane sextant curve, right? So if you compute the log canonical threshold of this pair, so the log canonical threshold is equal to 1/2. So by the interpolation, we'll know that this pair will be always K polystable when you vary the C from 0 to 1/2. So this pair will be destabilized when C is equal to 1/2. But in that case, it's in the log Calabi-Yau, I mean the module of log Calabi-Yau. So, but we don't have a uniform construction of that. But after that, if you consider the case when C is bigger than or equal to 1/2, you'll see the pairs given by the cone over elliptic curve as a surface and a minus K, I mean a general member in the minus 2K of this cone over elliptic and you will see this 2-to-1 map to a elliptic curve. That will recover all the bielliptic curves. So long story short, this pair, this bielliptic curve will be in the KSBA modular space instead of the K modular spaces, as well as this hyperelliptic curves. So this two will be in the KSBA modular spaces. Okay, in the last 5 minutes, I can tell you some relation of this modular space to the Hasse-Q problem. Remember, we have our Hasse-Q problem given by the mg bar of alpha equal to the approach of the second ring of the canonical plus alpha multiple of the boundary divisor. And if you vary this alpha, you can get different models. And in particular, we have the same phenomena as in the wall crossing in the, well, it's not exactly the same, but you still have this wall crossing structure. So you have finite many alpha i's such that you have this picture. And I can tell you what are known in general for the Hasse Q. So actually, we know very few of them. So three of the walls. The first three walls starting when alpha equal to 1, with mg bar of 1 is exactly mg bar, the module of the stable curve, the manifold stable curves. The first three walls are given by 9/11, 7/10, and 2/3. These are the first three walls. And when the genus equal to 2, all the walls were figured out by Hasse-Brennan. And when G equals 3, all the walls are all known by Hyun and Junyan Lee. But starting at the genus 4, we don't know all the walls. When G equal to 4, we know the case when alpha is bigger than or equal to 2/3 and less than or equal to 5 or 9. So we miss the wall when alpha is between these two numbers. And for this part, this is a work by Castaneda Martin, David Janssen, and Radulasa. When alpha is less than 5 or 9. And the other two cases we know is for genus 5 and 6. But we only know the last wall, the last minimum model. The last model. So for genus 5, this is given by Federchuk and David Smith. And for genus 6, this is given by Mueller. But we only know the last model. But the K-moduli space, the K-moduli we consider in this talk will give you more information about the Hasse Q for genus 6. So let's call this theorem C. So this is a pretty recent work. So when C, you choose a coefficient C to be between 0 and this special number, and you set this alpha of C to be given by a rational function. Then the upshot is the K-moduli space is isomorphic to the Hasse Q program for genus 6 curve, depending on this alpha, which is equal to alpha of C. In particular, the walls of the K-moduli space will give you the moduli, I mean the walls of the Hasse Q program, and in particular, we can find the last 6 walls or the minimum models or log canonical models. Which is 16/47 up to 47/134. There are 6 of them. Okay, so So in the last 1 minute, I want to give you a similar picture as I showed you in the perfect model for the genus 3 curve as before, right? So again, here, remember we consider the pair sigma comma c times capital C, where C, you can vary the C between 0 and 1, but when it's less than a half, then it is a log final pair. When it's bigger than a half, less than 1, this is a log general type, right? So let's consider on the left-hand side. When C is equal to 1, this is the KSB moduli. And by a junction, so this is by a junction, it will have a morphism to the M6 bar, the moduli of genus 6, the Riemann stable curves, which is also M6 bar of 1, the Hesse-Q model. And on the left-hand side, you have this K-moduli. When C is equal to epsilon. Actually, if you take the C equal to 0, then you only have the surface, which is a point. So if you want, you can consider the case when C is epsilon, but this is trivially, this is a point. And you have a morphism here given by the forgetful map. You forget about all the boundary divisor, but only preserve your surface, which is the smooth quintic de Pezzo. And here you have also a morphism, which is an isomorphism to M6 bar of (16/747) plus some epsilon, and you have also the contraction map. These two are trivial isomorphic because they are all points. And on the bottom, you have the Hesse-Q program to walk from the left to the right to the left when you increase your alpha. And on the top, in between, you have this F star, which is the moduli of K3 surface, which is expected to be the moduli of log Calabi-Yau varieties, or log Calabi-Yau pairs. But this is not constructed uniformly so far. But the upshot is you have this this wall crossing structure to connect the K-moduli to the moduli of log Calabi-Yau. And when you still increase your C, you'll go from the log Calabi-Yau to the KSB moduli. But the failure is for the wall crossing upstairs and downstairs, we don't have a one-to-one correspondence. So for this part we know by our work, and for this two parts, they are still missing. Okay, so that's all what I want to talk today. Thank you.